Well, thanks for joining us today, this afternoon. My name is Jun Wang. I'm one of the co-hosts for the CAS Colloquium series. CAS stands for Climate and Atmosphere Science and Engineering. It's really a grassroots effort that allows to exchange research in climate and atmosphere research. So today, I'm glad to introduce our speaker, our own Professor Charlie O. Stanier in our department here. Charlie probably is a professor that without any introduction, everybody knows him. Has been leading many projects recently of the Decarbon 2040, and he has also been studying a wide range of topics from the air quality to energy to pollution to climate change. And today, he's going to talk about a nexus of air quality, energy, climate, water, and agriculture in our region in the Midwest. So Charlie, you take away from here then.
Thanks, June. I want to shout out to June for leading the symposium series. It's been really interesting to hear all the speakers, and I'm thrilled to be one of them and share with you. So I'm talking about a project that is about 2/3 of the way through the Decarb 2040 project, and I list my co-Is and collaborators here. And I'll be sharing some work of a graduate student, Austin Doak, in chemical and biochemical engineering. So this is part of the first round of the seed grants by the VPR's office. And we're seeking to build communities on campus for convergence research. Our convergence strategy has three legs to our stool, if you will. We're looking at R&D, outreach, markets to mitigate carbon emissions and modernize our energy infrastructure. And the three legs of the stool are the energy technologies and systems, which is myself and Uday Kumar. And it's very important that we have, get my laser pointer going here. So the way we're thinking about these problems is we have to have the technologies. We have to understand where they should be implemented, and when they're implemented, what are the systems interactions, especially in the natural environment, that occur. And then do we have the finances, the business and consumer acceptance to implement these? We have a number of partners, which I've listed here on the right. And then in the chat, I put some links. One is if you want to get on our mailing lists, go to that Qualtrics link. And we have a small grant program that University of Iowa faculty can apply to. It's $50,000 total. And we're anticipating maybe 3-4 awards. And so something in the $12,000 to $17,000 range is what we're saying. They are due Feb 15, so get on those if you're interested. And mark your calendar for our 2-day decarbonization summit in April. And I just want to orient people in terms of climate research. You can have 4 bins, you can have more bins, but I've got 4 bins here. There's the climate science of how does the Earth system work. And I have a graphic by the Carmichael group here of biomass burning over South America and Asia to represent that. Then how do those changes to the climate system impact biological and human and economic systems? How can we adapt to those changes? And then what are the solutions that can reduce the severity of the impacts and keep the scale of the adaptation manageable? So Decarb 2040 and what I'm going to talk about today is mostly about solutions. I'm sure everybody's seen some version of this Ipcc emissions curve, where these are global CO2 equivalent emissions that are increasing kind of linearly. And then we have these pledges that companies and states and cities are making to rapidly decarbonize to net zero by something like 2040, 2050, 2060. So you see this so often, you kind of take it as an article of faith and forget where it comes from. And I'm going to tell you where it comes from. How are we doing on it here in Iowa? How can we do better? And what would this sort of net zero look like? It comes from the 1.5 degree Ipcc report. And I've got the full title listed: Mitigation Pathways Compatible with 1.5 degrees C in the Context of Sustainable Development. The key statement that has generated all these curves is, in model pathways with no or limited overshoot of 1.5 degrees C, global net anthropogenic CO2 declined by 45% from 2010 to 2030, reaching net zero around 2050. For those that may be not familiar, the 1.5 degrees C is the amount of warming over pre-industrial levels of, say, 1850 temperature. It's a very well-written report, and I think everyone should read that. And by the way, if there's any if you want full citations, we can email those to you. Just let me know or put it in the chat. Most of the things I'm citing, I've just listed the author, date, and journal name. So to get 45% decrease over 20 years requires a compounded annual change of 2.94%. And for Iowa, that looks like this, right? We're starting 2010 at 128 metric tons. There's your 2.9% decrease per year. There's your Ipcc aligned decrease. That's how we're doing on that. These are the official DNR estimates following the EPA procedures. There's the COVID year with 2020, when we had significantly less transportation. So that led to less emissions. DNR has not released the 2021. That won't come out for another 11 months. But the Rhodium Group has a national estimate of the size of the rebound, and that's about 6.2. So I've applied the 6.2% increase from the Rhodium Group to get an Iowa estimate, run a percent decrease through that, and that's about 0.85, or we've decreased it about 1% per year. And so to catch up, you could look at it that we need to do 5.5% per year for the next 9 years if we want to still make that target. So to summarize, this is what we needed to do, decrease it about 3% per year. This is what we actually did. And this would be the catch-up rate. So this isn't the first time people have looked at these curves. So I don't know if Jerry's on, but Jerry Schnur chaired the Iowa Climate Change Action Committee. Iowa Climate Change Advisory Council, ICAC, in 2008, 13 years ago. And they have this in there, right? History since 1990. A business as usual future in blue and red with two slightly different businesses in the future. They had a plan, a bundle of actions and legislative actions and things companies and consumers could do. That's the green curve. And then the black dotted line, I drew that in, that's what we actually did. This is that, I call it the playbook. the 2008 Playbook. This is a marginal cost curve. And the point here is that each of these acronyms was a policy action. Educate people, have a renewable fuel standard, put a price on carbon, et cetera, et cetera. Each of them had a cost. Things that were below zero would save money if implemented. Things above zero would cost money if implemented. And if you implemented all of them, right, you'd have a 70% reduction relative to the business as usual 2020. Another good read to go back and visit. So a slightly different view of this is that we've got now Iowa's per person emissions which peaked in 2010 and have been slowly decreasing. National emissions are about half that and have been decreasing somewhat faster. And then the dotted lines are these pledges that people are making to get to close to zero by 2040. The sectoral breakdown is over here on the right and might surprise people. The largest ones are not electric power and transportation, but instead residential, commercial, industrial fuel use. So this is natural gas and propane for heating and for steam generation, and agricultural emissions. Finally, I'm putting in valuations, and these are using social cost of carbon of $52 per ton, which is the US EPA value. So you can think of this as the damage to the environment, to our economy, that these emissions are doing. You can also flip it and say this is the opportunity to get paid to reduce. Now, in actuality, we're sort of transferring money between our different actors within society when we do that. So here's a different view of that playbook that's more readable. And my point is there's a lot of solutions that we have on the table now and that we had on the table in 2008. And I've organized them using the same positions and color codes as the emissions pie. So the gray is the industrial fuel use and residential fuel use. The blue is the transportation, the electricity is in this peach, the ags in green, the others in yellow, and things that didn't fit anywhere are over here on the left in white. And I'm going to be referring to this throughout the talk. So let's go sector by sector. Electricity production is kind of Iowa's gold star. It dropped at 8% per year. And it was a pretty big piece. Now it's an increasingly small piece of our emissions pie. 57% wind, 24% coal. Solar just broke the zero mark in 2020 and 2021. So how did we do that? Well, there were federal requirements under the Clean Air Act that caused fuel switching, right? So that the requirements to burn coal without polluting the air were increasing the cost of coal. Relative pricing between coal, natural gas, and wind had a lot to do with that fuel switching. So I'm noting what we did in red. We did fuel switching from coal to natural gas and coal to wind, and we increased the wind power a lot. The major ICAC recommendations from Jerry Schnoor's 2008 report were not implemented. So it didn't go as planned. The plan was an emission cap, a regional trading market, and build one large new nuclear plant, right? What we did, in fact, was fracking came along, made natural gas cheap, and we had tax incentives that helped us invest heavily in wind, and the cost benefit and environmental benefits of wind were substantial. Going to the next sector, transportation, 15% of the total. On-road vehicles are 80%, other vehicles are 20%. This is growing, well, it's flat, right? 0.1% per year. So the story there, sorry, I forgot to change the text at the top. The story is marked in yellow and red here at the bottom. We did a lot of liquid biofuels. We did not make them from perennials and cellulosic. We made them from corn ethanol. We created efficient vehicles, but did not adopt them. We created electric vehicles, but limited adoption. The plan was reduce vehicles miles traveled, we've actually increased. And so these factors all taken together keep us flat on the transportation side. Here's some of the backup to that. The vehicle miles traveled in Iowa is in blue. And you can see the general increase, the COVID year in 2020 when we drove less. And then you can see national, I don't have the Iowa numbers, I have national fleet miles per gallon in orange, right? And it's basically stuck at 22 miles per gallon for the fleet. So what's going on there is we are creating new vehicles that are much more efficient at creating motion from energy, but horsepower, vehicle weight, and vehicle area, the area that it takes up on the road, are all at all-time highs. So we have more efficient vehicles, but they're much larger and more powerful, and that's leaving us at this sort of flat condition. Next sector is agriculture. You see these two big green blocks. 29% of the total, it's increasing at 1.4% per year. The nitrous oxide is coming from our cropping systems mostly. And I'll talk more about sources. The methane is almost entirely from livestock, half of it from the manure, and half of it from enteric fermentation that's happening in the stomachs of ruminant animals, and most of our ruminant animals in Iowa are cattle. That's not the only emissions associated with agriculture. There's a bunch of other emissions associated with agriculture, but the way the Iowa DNR breaks them down, they're in other pieces. So the tractor fuel is in transportation, the emissions of carbon dioxide from ammonia manufacturers in other, the fuel required to make hydrogen, to make ammonia, to make fertilizer is in the residential, commercial, industrial, as is the fuel for all the grain processing. So what did we do from the playbook for agriculture? We did a lot of biofuels. We did a little bit on the biorenewable feedstocks, so making chemicals from plants, plastics, Nature Works, PLA, these plastics from corn. And that's about it. That's about all we did in terms of trying to do climate smart agriculture. So I put it in bold. Liquid biofuels, kind of the only thing we did. There's plans now for some other things that I put non-bolded: low carbon ammonia, BECCS, bioenergy plus carbon capture and sequestration. So that's capturing CO2 from the ethanol plants, putting it in a pipeline, putting that in geologic storage, making gaseous fuels from manure, and redoubling our efforts at soil carbon storage. So I'm going to back up sort of my statement that we didn't do a lot in terms of climate smart agriculture. Here's, somebody should send me the Iowa data. This is National Conservation Reserve Program acreage. That's decreasing. Where is it decreasing? It's decreasing in a lot of places. The yellow, orange, red, and maroon are all decrease. The green is increase. So it's decreasing in most counties in Iowa and throughout the Corn Belt. So looking in to N2O a little bit. So this is 17% of our total. Where does it come from? We put ammonia and urea down as fertilizer, and it's biologically processed through a chain that leads to the nitrate that the plant needs. But if it goes too far, it can reach NO and N2O through denitrification. So these are complex microbial processes that depend on the microbial communities, the soil conditions, the amount of water, the pH. And 28% of it is coming from applied fertilizer, and then in the water, that's high nitrate water that's coming off of those fields. Some of it comes from nitrogen fixing crops because those crops are doing this process, and some of it gets on this side channel and turned into N2O. Some from manure, some from decay of crop residue. And it's thought to be slightly increasing over time. Methane, half of it from manure management and half of it from that enteric fermentation. There are a series of best management practices that I'll talk about in a little bit. So these are like kind of invisible gases present in low concentrations with no odor themselves. So how do we know this is all real? My group takes samples as part of a large international cooperative network from a tall tower in West Branch, Iowa. And so gas is sampled at the top, pumped down, and analyzed for 60 species. One of those is N2O, nitrous oxide. One of them is methane. Nate Massa is the student who's working on that lately. And we go out, rain or shine, deep. It's on the top of the hill. In hindsight, we should not have put it on the top of the hill. It's a television tower that serves as the sampling location. These are the concentrations of N2O and methane, and they are increasing. We started in 2007. So this is a, 15-year record. They're both N2O and methane are increasing. The orange is just a provisional data that hasn't been finalized through all its QA/QC checks. But all this tells us these are both fairly long-lived gases, right? So this says just sources exceed sinks in the Northern Hemisphere. It doesn't say where the emissions are coming from. We have to do more work to tell that. So here's some of the clues of where it's coming from. We have increasing acreage in corn in Iowa, long-term increasing soybeans, last 20 years decreasing soybeans, and we are applying more fertilizer. So this is a time series of nitrogen applications since the early 60s from the Lou group at Iowa State. This is national, but where is it being applied? It's mainly being applied in the Corn Belt. We can see the nitrogen leakage. So here's Chris Jones's work. Here's megagrams of nitrogen in the Mississippi outflow. The total is the green. Total minus Iowa is the blue. Therefore, the gap between the green and the blue is Iowa's contribution, which is growing in his assessment. We can see ammonia in air is increasing, and it looks like a small increase. It was a logarithmic scale. It's actually a pretty substantial increase in gas phase ammonia from long-term measurement networks. Ammonium in rainwater is also increasing. The N2O, how do we know it's coming from Iowa? You look at the vertical profile. So this is the surface to 8 kilometers. Each dot is an aircraft flight. So we sample from the tower, but then NOAA, who we work with, has a light aircraft that flies monthly or bi-monthly profiles. And they take a sample of gas at 1,000 meters, at 2,000 meters, at 3,000 meters. For things that are being emitted at the surface, you see an enhancement at the surface. And so I'm comparing a site in California that's influenced by the Pacific Ocean versus Iowa for N2O. And you see this large enhancement in N2O at the surface from March until June. It's the strongest. So this is a very strong sign that we are a source of N2O, just like we would anticipate from our fertilizer use and our field scale studies that measure N2O at the plant level and at the field level. You can fly an aircraft around the Midwest during the growing season, and when you drop down in altitude, you see a big increase in N2O. And you can compare this amount of increase to what the models would predict. And usually, every paper I'm finding needs an increase to the inventory to make a match. This was an increase of 6 or 3-fold. As I said, we know the total, the net is well constrained because there's only one sort of global net emission that gives us this increase rate. But we could have the sources and the sinks off. And there's a lot of evidence that we do. Methane, kind of same thing, except it's seen at low altitude year round in Iowa. Not so much near the Pacific Ocean. And the animal census data makes sense with the trends that we see from the aircraft and the tower. We have increasing cattle, increasing hog, and increasing poultry. So one of the arrows in the quiver, or one of the things in the playbook, is voluntary markets. And I highly recommend the ISU's summary of these agricultural markets. And I'm just listing 1, 2, 3, 4, there's about 12 markets that they covered. And these are nonprofits or companies that are trying to develop protocols to monetize the emissions reductions that are obviously possible in agriculture. So they want to serve as the verifier and the middleman, if you will, between either government or private actors that would like to see an emission reduction, and then the farmers who can deliver that. And I'll just show you one example. It's difficult to verify this stuff, and the emissions reductions are kind of uncertain. But here's, if we believe this curve, that the relationship between fertilizer application and N2O emissions follows this curve, the producer reduces their fertilizer application. The system responds by emitting less N2O. That creates the environmental benefit of less nitrous oxide emissions. And then that gets monetized, farmer gets paid. You can work through the numbers pretty easily. This specific example would work out to $5 per acre at the EPA's social cost of carbon. However, for corn at 200 bushels, $6, I should say corn, that's $1,200 an acre in gross sales. So, you know, it's not a big incentive. If you stack this benefit with other benefits that you would get to water quality, for example, maybe this could be a go. The form that you have to fill out to establish your baseline and then to verify your actions it looks like a tax form, and it's pages and pages of information about your farming practices. And so the challenge for these market programs is how to make that, how to strike a balance between feasibility and producer acceptance on the one side, verifiability on the other side, and keeping the transaction costs down. Because if people are spending, days filling out forms, and then somebody else spends days taking soil samples and air samples and verifying that all the things that were marked on the form actually happened on the farm, then it's not going to work. I have a few more notes on methane and nitrous oxide. We have consistently underestimated sources in government emission factors for both of these gases. As I said, the net emissions are well constrained by the global measurement network, but the individual balance of sources and sinks are not. Iowa is a source for both. And then the other issue is that this is made using 100-year global warming potential for methane, but methane only has about a 12-year lifetime. And the critical period to stabilize the temperature is between now and 2040 or 2050. So this issue of discounting the fact that methane is not going to be here for that full time is what we're doing now when we use the existing Iowa DNRs using a global warming potential or a multiplier relative to carbon dioxide of 25. Excellent paper out about 2 weeks ago argues for a new set of global warming potentials called GWP 1.5 degree. And so these are optimized to hit that overshoot of 1.5 degrees by 2050. In that framework, the global warming potential for methane should be 75 or 3 times what it is currently. So we can redraw this pie now. There's a good chance that we're underestimating our N2O emissions by a factor of possibly 2 or 3. And then if we change our global warming potential for methane from 25 to 75 and account for the fact that we often underestimate these sources, we get these larger pieces. Not all methane is agriculture, so I had to put in a little extra here. So the policy actions that we would take in this world are a little different and emphasize the importance of constraining these emissions further and dealing with them should they be where they think they are or even larger. So that's what I had to say on ag. Moving to the RCI, the residential, commercial, industrial fuel use. 29% of our total, this is propane and natural gas usage. This is growing at 1% per year. It's, mostly CO2 from combustion. There is some nitrous oxide and some methane that are emitted from combustion. And then there's some methane that leaks throughout the whole system. So it's 74% industrial, shown by the green here. That's increasing the fastest. And then the residential and commercial are 15 and 11% respectively. So we had our solutions playbook. Why did these go up? Well, we had some new industries come, which is great for Iowa. But I list these things that we did, but we kind of did them not very aggressively. Efficient buildings. We actually reduced the energy efficiency program in Iowa substantially in, I think it was 2018, that was scaled back. We did a little bit of solid biofuels, a little bit of waste to energy. I don't want to discount the energy efficiency things that are happening on the ground, but they're not showing up in the overall numbers to the extent that we would like or that we think they could. And we did some building electrification through heat pumps. So looking at these options in a little more detail, what do we, I looked at a permit application yesterday for a new soybean crush plant in Northwest Iowa, $375 million plant. And I said, what are they going to use to run their boiler? Natural gas is what's proposed. They need a lot of steam to run that plant. What option do they have other than natural gas? Well, this is a mix of some residential, some low temperature, some high temperature, but they could use biofuels. You could take manure and digest it to make the methane. They could use electricity. They could use hydrogen. They could use ethanol. There's some different options. At the residential level, it's mainly building electrification through heat pumps is the thing we've mostly been thinking of, as well as some solar. Or the other route is to keep using natural gas, keep those pipes plumbed to our homes, but get the gas from a different method that's carbon neutral. Every one of these has pretty substantial barriers, and I'm not going to go through every barrier, but my pitch is we need to get together, Iowa State, other universities, and go through this in more detail. I know Mark Embaugh-Wright has been doing this, and we'd like to join and add the social, business, finance, and user adoption angles that we've been working on through decarb. All of these have market regulatory uncertainty and lock-in issues. Players don't want to move until they know what the market's going to be. And right now that's highly uncertain. So we'll talk a little bit about hydrogen. For you that don't know, we've got different colors of hydrogen. Traditionally made hydrogen is called gray hydrogen, where we take currently natural gas, has CH4. We split it in complicated chemical factories. We want the H to make ammonia, NH3, and we are currently discarding the CO2. There are currently signed agreements to do blue hydrogen in Iowa, where that carbon would be captured, put in a pipeline, and then put into geological storage. And then you see a lot of news about green hydrogen right now, which is to use solar electricity. So you make green power and then do some process, usually water electrolysis, to get hydrogen. A few examples in this RCI space. Here's a PV panel, but PV panels get hot, and so you can harness that heat through solar water heating or solar brine heating, depending on what temperatures you're going to. And this is the kind of construction that's needed to do that. Hydrogen boilers, right, are being marketed by Bosch, which is funny. Bosch was involved in the original invention of the Haber-Bosch ammonia process. But so you can burn hydrogen. It has some significant disadvantages. Very wide explosivity limit, only a third of the volumetric energy density, very high temperature, high velocity flame. That high temperature makes a lot of thermal NOx. burns invisibly, and diffuses through most metals and embrittles most metals. So you need a lot of special equipment to make this happen. Electric boilers are also being sold. So think of your home water heater with its electric coil, but now this is now going to replace the gas in a boiler, or they have dual systems that could run on gas or electricity, depending on which is cheaper at the moment. Heat pumps, residential ground loop heat pump, often called geothermal here in Iowa. So now it's summertime. We'll start with summertime, right? It's hot outside and you use a pump of fluid through the ground. Now I have this nice cool fluid and I use that as the waste heat sink for this building. And that's a lot more efficient than using the air as a waste heat sink, which is what a typical, outdoor AC unit would do. So they can be more energy efficient, but they have the increased capital cost of putting all this underground piping in. In wintertime, you run it in reverse. You draw heat from the ground and then pump that into your house. The heating COP for wintertime is the heat delivered divided by the electricity input. And real systems, some of them measured by Iowa State, have seasonally average COPs about 3 to 4. So you can put in 1 unit of electricity and get 4 units of heat. If that electricity is carbon free, then I'm heating my home carbon free. This class of technologies also includes these increasingly popular mini split or ductless systems that have their outdoor unit here, their indoor unit here. So there's no duct connecting your air handler in the basement, for example, to your vents. And so that adds more efficiency because you're not losing energy along the way. The problem is, I got to walk you through this slightly complicated graph. So this is time. And let's start with gas prices in red, all inflation adjusted. So gas, when that ICAC report was written, was at $14, and then it dropped to $8 by 2019. It spiked back up lately, but a 42% drop in the price of gas, a 10% increase in the price of electricity. And this has flipped the competitiveness of these heat pump systems. So the green line is the COP required for price break even, right? And I said real systems are 3 to 4, right? And in 2008, all you needed was 2.4 to break even. And now you need 4.5, which doesn't exist to break even. And this is just saying the same story that I just told. So because natural gas is cheap and electricity is a little more expensive than it was in 2008 in Iowa, the economics of installing these have flipped. And for example, the large medical building that's part of the UIHC campus considered both natural gas heat, heat pump heat. And on price basis, they installed just a standard natural gas heating system. The other problem with these is that the heat pumps work worst when it's coldest out. And so you get a few days each year. If everybody did this, if we all scrapped our furnaces and went to heat pumps, you get a few days each winter with very high electrical demand. And if you work out the numbers, we're currently summer peaking for electricity at 9 gigawatts. If we all switch to heat pumps, we become winter peaking at about 27 gigawatts. So our peak generation needs to increase by a factor of 3. If we do that with renewables without storage, then we can't count on them when we need them. So we have to add storage. The amount of storage that we would need is just kind of mind-blowing. So it's all just too complicated. We need a backstop. And Mark might have better numbers on this backstop, but let's say we just wanted to keep doing what we're doing, right? And suck enough CO2 out of the air, put it in a carbon pipeline, inject it into deep geological storage. And then all the people and all the all the activities in these sectors don't have to worry about it. Just have to pay a little bit to do this technology. So what would that look like? And this is not a joke, right? And I didn't write the headline. This is the headline from Carbon Engineering Magazine. And this is an artist's rendering of a carbon capture facility like I'm talking about. And we've got the pipelines proposed as well. So if you just add up the carbon from these sectors and say it's too messy to deal with them, I need 60 megatons CO2e per year sucked out of the air. And I need renewable electricity to power all that. And I'm not going to worry about intermittent. I'm just going to overbuild the system. It's going to run when the wind blows and the sun shines. What would that look like? Here are my sources for the numbers. Key is like, how efficiently can you do this? And I liked the approach of House et al. And PNAS, who looked at how efficient are existing mature acid gas separation systems. And he finds they can reach about 5% of their theoretical minimum energy. So if it takes 20 megajoules per gram or mole or whatever, then it's going to take 20 times that to do it in the real world. You can get closer to the theoretical minimum, but then you have to build everything bigger. It's this balance between capital and operating costs. Here's what it looks like. If I use the lowest capital cost in the review literature, in peer-reviewed literature, if you go to random websites of companies that say that they're going to do this and they're looking for investors, you'll find like really low numbers. But if I use peer-reviewed numbers, I need a $66 billion, this isn't national, this is Iowa investment. The initial capital cost per Iowan is $21,000. Annualized costs are here as shown. Annualized cost per Iowan to do this would be about $3,800. And it works out to a removal cost of $198 per metric ton of CO2e. If you use realistic numbers instead of the lowest, you don't even want to look at the numbers. This would require 152 million megawatt hours of wind or solar or renewable. We currently have 34. And the construction project itself would just be so enormous. It's the materials and the people required to do this are difficult to imagine. This is one $3 billion ammonia plant. It's enormous, right? You can't, these little dots are cars over here. We build 22 of these and increase our low carbon energy supply by 450% to run them. So I know there's more favorable assessments, but I'm just trying to give an idea of what that would look like and why we need to thread the needle and find the more efficient technologies and deal with this long list of barriers here. So, you know, we got to get together and come up with the technology and the policy and the education for people to make it happen. So my takeaway points, I keep coming back to this 2008 plan. We achieved 14% reduction from the baseline, but it didn't happen as planned. The plan was cellulosic ethanol and energy efficiency were the major sort of things that would save money and reduce a lot of carbon. That's not what happened. And so now I have a longer list of takeaway points. The efficiency gains that group mentioned, the 20% reduction just from making our homes and factories more efficient, that's still out there. Short-lived climate forcers, methane, and some other gases I didn't talk to are an obvious target to go after. We have success stories, ozone depleting substances, ambient air quality, the success of the 8% per year in the electricity sector. So what lessons can we learn for the rest of the system? Voluntary measures were not adopted. Behavior changes were not adopted. The lack of carbon pricing combined with these other lacks made for very slow action because the market's not there to sort out the winners and losers. And government committees, I think, are really bad at determining winners and losers. You know, what's going to be the efficient, low-cost solutions. All the solutions that required expensive natural gas and oil to work, that doesn't apply now. All the solutions that require very large renewable electricity, it's going to take time to build that. All the solutions that require a lot of land are tricky. Some of the predictions of prices decreasing with scale worked out and others didn't. There's a huge number of technologies, as I kind of showed you the tip of the iceberg, that are kind of waiting in the wings. And I think with modest carbon pricing, they'll be unleashed and the market will start sorting this out. And I think we need to redo that marginal cost curve in a convergence science approach, thinking more about the social adoptability of these technologies. And I hope there's some questions.
Thank you, Charlie. It's really a wonderful talk. I know I've been colleague for 6 years, and this is really my first time listen to your 1 hour seminar. So I learned a lot. So before we open the floor for questions, I just want to say the CAS is really a platform to allow us to exchange our opinions, research, and ideas. It is by design, we try to do everything online. So we are saving the carbon footprint. We are. And we are being successful doing that in the pandemic in the past 12 months without invite anybody in person. And we are able to do this more or less every month, a seminar on this. So if you want to chime in to give us a talk to share with your colleagues, you are more than welcome to do so. And you can be the host. If there are any other people you want to invite and to share the research frontier or economics associated with the climate change, you are also welcome to do so. So anyway, with that, I'm going to stop the recording, but I think we should give a great applause to Charlie for the great talk.